Hey, good morning, guys. We're starting Chapter 6 here, Differential Equations and Mathematical Modeling, Section 6.1a, Solving Differential Equations Algebraically. And basically, all solving differential equations means is finding antiderivatives. So what I have up here is what am I expected to remember from the fall, early winter, when we were doing all our derivatives, and all of these functions, remember, have the chain rule where u is a differentiable function of x. So what I did is there's actually a PDF place that it's learning that you can print one of these out for your own, but you need to know all of these derivatives, and if from left to right, they're derivatives, from right to left, they're going to be integrals. And these chain rules, okay, we're going to do a couple today, and there's going to be, later on, we're going to learn something called substitution. Helps us deal with that chain rule a little bit better and a little bit easier, but that du, actually, when I integrate, that little bugger gets sucked right back into the function, back to the antiderivative, okay? But that's all we're going to be doing is, print these off. If you were here, I would be able to hand you a sheet of them. And if you're coming next week, I can give you a sheet, or you can print them off right now. But if you're 100% virtual, you're going to have to print your own sheet. And, like I said earlier in the year, okay, if you don't know your derivatives, this is going to get rather hard when we do integrals, okay? Sorry, I did say that earlier, but if you do not know your foundational derivatives, integrals are going to be a bear, and you're going to have to work twice as hard. So get these little buggers memorized, okay? As we continue on here, natural log. Okay, natural log antiderivatives are difficult to see sometimes. So this is what I'm talking about with the chain rule. Well, think of it. If y equals the natural log of x cubed minus 5, okay, then we know its derivative y prime is going to equal 3x squared over x cubed minus 5, because the derivative of a natural log is, basically, it's the derivative of the business divided by the business, okay? And then a lot of times we reduce, if we can. You're not always able to reduce, okay? But now what's going to happen is you're going to be asked a different question. They're going to say, oh, if dy dx equals 3x squared over x cubed minus 5, then what does my original function equal? And we need to reverse here, okay? We need to go backwards. The antiderivative of dy dx, well, that would be y. That would be the antiderivative of dy dx, would be y. And I need to be able to see and understand how this gets absorbed back into that, because the chain rule, when I differentiate, remember, it's the derivative of the business divided by the business. So the business gets absorbed, the derivative of the business gets absorbed, and sometimes we may have to multiply or divide, not divide. Sometimes we're going to have to multiply by a constant just to make things work, okay? So bottom line, what are we doing? We are reversing the process today. And what do you mean by multiply by a constant to make things work out? Well, here's what I mean. And you might not understand this right away, but if this were a 6x squared on the top, well, then that's going to be a 2 out in front of the log, because it would have been 2 times the derivative of that log to get that 6x squared on the top. Also, when I'm looking at logs, another thing I want to see is, another common thing to identify is the power in the top is exactly 1 less than the power in the bottom. And that is due to your chain rule, that is due to the derivative of this getting popped in the top a lot of the time, okay? So that's where we're going to go. We're going to run with some of these here. And like I said, solving differential equations algebraically, it just means, given a derivative, find a function from which it was derived from. Find the original f, okay? And this is find all of the functions. Now, what do you mean all? Remember, they were vertically translated by constant c, okay? And you're going to have to work at these. Some of these are going to start easy, and then they're going to progressively get harder. You're going to get very frustrated. You're going to want to throw things, and you're going to get upset saying, I can't do this, and I'm not going to get there. I'm never going to get there, and you are. You need to work at it. This is stuff that you have to practice. You have to work at. It's not watch a video and absorb it for 99.9% of the population. You need to work and do examples, okay? So also, we are going to be doing these differential equations 3 different ways. Today we're going to be doing them algebraically. Tomorrow we're going to be doing them graphically, and that would be they're called slope fields. We'll be solving a thing called a slope field. They're kind of crazy little looking critters. And we will also do a difficult one next week, and I promise you this will be on a pre-response test on the AP test, where it's called separation of variables, where you're going to be given a derivative in terms of both x and y. You're going to have x's and y's in the same equation, and you're going to have to separate all the x's and y's to opposite sides of the equation. Then you can find antiderivatives and try to solve them, okay? Those are the most complicated ones. But all we're really doing is we're algebraically finding these. Well, so they are all solving differential equations. If I can say it one more time, that is just saying finding antiderivatives. And that's what we are going to be doing. And I want all of the functions. Okay? At the end, we will find particular functions. So what is the antiderivative of dy dx? That would be y equals the antiderivative. And this is where we're playing with the constant. Remember, if this is a polynomial, well, derivative subtract 1, so we're going to add 1 to the top. And then we're like, okay, well, what do we multiply in front of the x by 3 to get a 1 there? Oh, that would be a third. Okay, and then minus. Well, this is an x to the first. That means it comes from an x squared. Okay, and typically the number we want goes in the numerator, and the number we don't want goes in the denominator. So when I multiply by 3 over 2, the 2's cancel, and I'm left with just a 3. And then this is going to be plus. Plus, usually we're going to be looking at this, and we're going to say, ooh, this is x to the negative 1. Well, if I add a power to x to the negative 1, I'm going to get x to the 0, which means I had no x's. Ooh, what's going on there? That is where your natural log of x comes out, and it's technically an absolute value of x. You don't know why that is yet, but that's okay. Anytime I'm, 99% of the time I'm going to do, I'm not going to leave I'll leave the absolute value out for now. It doesn't really matter. And then remember, we want all the functions, so there was always some constant at the end that we added. And then, if you're actually doing these to the best of your ability, ladies and gentlemen, you are checking them, and you're going to say, oh, derivative of y is dy dx. And that's going to give me the derivative of 1/3 x cubed. That's going to give me an x squared minus the derivative of 3 halves. That's going to give me 3x. Plus the derivative of the business over the business, and the derivative of my constant goes away. And when you take the derivative of your antiderivative, that is how you check to ensure you're correct. And then you circle your answer to say, hey, there are all my solutions, all right? And they're going to start easy, like I said. They're going to slowly get a bit more difficult, okay? So hopefully you printed that sheet off, and what we're going to do is we're finding all antiderivatives. Well, the left side's easy, dy dx. The antiderivative of that is y. The derivative of e to the x is e to the x. Therefore, the antiderivative of e to the x is e to the x. There is a chain rule pulling through here, but we don't see it yet. We will at the end of the lesson. And the antiderivative of secant tangent, well, the derivative of a secant is a secant tangent. So the antiderivative of those two multiplied together is going to be a secant x. And I'm keeping on going. Sorry, I had to shut that one off. I don't know who this is, but it doesn't matter. And then don't forget, we want all solutions, so all of these are going to have a plus c at the end, and then you check them out. You don't have to write dy dx, you can call it y prime. The derivative of y is y prime. That notation is one and the same. The derivative of e to the x is e to the x times the derivative of the exponent, which would be times 1, so that doesn't affect it, minus the derivative of secant something is secant something tangent something times the derivative of my something. So those ones don't affect anything for me here. And notice if I take the derivative of what I just anti-differentiated, I get right back where I started. That is how you check to make sure your derivatives are correct. Don't just type them into your CAS. Okay, we can, but you need to make sure these things get done correctly. This is a very important skill. Okay, find all functions y that satisfy this. Well, to be honest, before I even move on here, now this is a goofy looking critter, but that's going to look like one of those templates that we have on that page, 1 over 1 minus something squared underneath the square root. That sounds like an inverse sine, okay? So we're going to be looking at this basically dy dx. Let me get to where I'm going to be first. I'm going to leave this just as it is because I can see I'm going to identify that as an inverse sine minus, well, I really don't like this here, so I'm going to see this as x to the negative 1/2 power. If I can ever see my exponents so I can anti-differentiate and just add 1 to them, that's what I want to see. Okay, so my y is going to, that's a bad y, sorry, but my y is going to be, if you're looking on that sheet that I had in the beginning, hopefully you printed it off, you're going to be able to cross-reference this to an inverse sine. It's not an inverse cosine because the inverse cosine should have a negative 1 on top, okay? So this is going to be the inverse sine of x minus, well, what do we got here? Well, x to the negative 1/2, if I add a half to that exponent, that's where I get. And then I'm thinking, oh, what goes in front of the x that I multiply times a half such that I get a 1? That would be a 2 plus, okay, then I'm thinking here, ooh, this is an x. If I add 1 to that 3, that's a negative 2. What do I multiply times negative 2 in front of that x to get a positive 1? Looks like I need to change a sign here, doesn't it? Looks like I need to make this a minus 1/2, because if I take negative 1/2 times 2, that gives me that positive 1. And I don't have to write these derivatives all out. I can check them right here as I'm moving along. And don't forget, I want all functions of y that satisfy this differential equation. And there's an infinite number of them that are vertically shifted. Okay, so then we get to there. You can leave it like that. Or you could say y equals the inverse sine of x minus 2 square root of x minus 1 over 2x squared plus c is another way to roll with that one there. Wait a minute. Back it up here, Kruger. That's not an 8. Why would you make that a negative 3? That was supposed to be a negative 2, which is going to change some stuff here. Hey, good thing I checked it, because that's going to give me this. If I add 1 to negative 2, that gives me negative 1. Well, now I need a positive 1, so that's just really a 1 in front of there, which changes that dirty little rascal to minus 1 over x, and I could write my solution like that as well. Okay? And I encourage you, I don't know, I'm going to check to see if I have that one changed in your note packet or not, number 4. Okay, I see it is changed in there. I do honestly encourage you over these next couple, hit pause, give it a shot, okay? At least this one. And see where you're at, and you're going to be cross-referencing, because, you know, I understand this is going to be hard. We haven't done them for a while. Hey, this right here, this is an inverse tangent of x. Oh, yes, it is. And that's a y. And then I can see this power is 4. Well, that means it's coming from a 3. That minus is there. And so, oh no, I got to add 1 to it. Come on, going the wrong direction. So I got to add 1 to it. So that's going to put me at a 5. What do I multiply times 5 to get a negative 5? Oh, that's going to be that just right like it is. Plus what? Well, hey, check it out. This is really an x to the 0. Notice these are 1 off. That's a 1 there. Okay, so this is really going to turn into a 3 ln x plus 1, and then there's my constant. Okay. Whoa, how did you get that? Well, when I'm thinking about this, this is going to be 3 times the derivative of my business over my business, which is 3 over x plus 1. And I get right back to there. So that's where I am at. Whoa, wanted my eraser. No, there we are. Okay, now these next couple, these are chain rule derivatives, okay? What do you mean they're chain rule derivatives? Well, they're chain rules. Think of this now. Whoa, I didn't want to do that. Where did this little bugger come from now? Well, think about this now. If I had e to the sine x, and I had, that was y equals, what is my derivative of that? Remember, it was e to the something, to the sine x, times the derivative of the something. Derivative of sine is cosine x. So this something is coming out of the chain rule of that e to a function of x. So this is going to be y equals e to the sine t. And then when I take the derivative, I don't need to do this because I can see I just did it, and that's where that cosine t comes from, okay? So let's give the next one a shot here. Remember, all of your trig functions had the chain rule. Thinking derivatives, just look right here. The derivative of x to the 4th is 4x to the 3rd. The kicker is it's an x to the 3rd. That 8x to the 3rd is coming out somehow, some way in the chain rule. So as I am differentiating, antiderivative of sine is what? Derivative of cosine is negative sine. So that means this would be a negative cosine of an x to the 4th. Okay? And then, ooh, that absorbs. But notice the derivative of this is 4x to the 3rd. I need 8x to the 3rd. Maybe there was just a 2 out in front of it. Well, let's check it out. To see, that's that adding of the constant. Well, what is the derivative? Y prime is going to equal negative 2 times the derivative of cosine something is negative sine of that something times the derivative of that something. Well, I can see negative 2 times negative 1 times 4x cubed. That gives me 8x to the 3rd sine x to the 4th. And I can take the derivative of what I found, and notice I'm getting exactly where I started from before, which means my antiderivative right there is almost correct. It's almost correct. Remember, we wanted all functions, all of them, so I need a plus c. I need a plus c on all of my antiderivatives, just so we know this, okay? Well, that's okay. That's going to be my plus c. Let's go to number 7. Okay? So what we're going to do is there's all kinds, you're going to have chain rules going in through here, okay? So we're going to solve the initial value problem, okay? Solve the initial value problem. That means find the specific solution to the given equation. Okay, the specific, because they gave me an initial condition. They gave me a condition that it has to meet. And of all those infinite functions shifted up and down c units, only one of those c values is going to go through this point. So we're going to start this out first by finding our antiderivative. Okay, well, this is going to be y equals, the derivative of e to the x is e to the x, so this is going to be 2e to the x. And notice, as I'm going, my mind is taking the derivative of 2e to the x, and it gets 2e to the x. So I'm differentiating what I'm anti-differentiating right away, and I'm checking things. So what is the derivative, antiderivative of negative cosine? Well, the derivative of sine gives me cosine, so maybe that's minus a sine x. Well, the derivative of sine is cosine, so I can see these come through, but I need all of them first, okay? And then after I have them all, I'm going to plug in my 2e to the 0 minus sine of 0 plus c. That's going to equal my y value of 3. And I'm going to solve for this guy. So that's going to be 3 equals, well, e to the 0 is 1 times 2 is 2, minus the sine of 0. What's the sine of 0? It's 0 plus c. So c must be equaling 1. That means my particular solution here, y, is going to equal 2e to the x minus sine x. Ooh, that's a bad sign. I don't like it. Minus sine x. And that c value is plus 1. We did this earlier this year. We found some particular solutions. So whenever they give us an initial condition or an initial value, we need to calculate this specific value c. In this case, it was 1, and tag it at the end of it. Okay. So what you're going to do is, hopefully you're working on number 8 now here, and give her a shot. And I'm going to be looking at this. Oh, this is a derivative of a. Well, dA over dx, antiderivative of that is going to be a big A. Well, I can see this as x to the 9th. That came from an x to the 10th. 10 times 1, so that 1 must stay there. Plus, well, that's an x to the 4th. That means that came from, oh, this one's working out really nice. Minus, that's coming from an x squared. Oh, boy, when the coefficient is 1 bigger than your power, that's kind of sweet because it gets absorbed right up. Plus 4x plus some value c. Well, they're telling us a is 6 when x is 1. Okay, well, if a is 6 when x is 1, well, 1 to the 10th is 1, plus 1 to the 5th is 1, minus 1 squared is 1, plus 4 times 1 is 4, plus c, and I can see these are going away, so I can see c is going to equal, well, there's 5, and if I subtract it across, c is going to equal 1 again. So my particular solution, a, is going to equal x to the 10th plus x to the 5th minus x squared plus 4x plus 1. Looks like c is must always be 1, right? No, it's not. You didn't want to evaluate anything bigger than 1 in there with that x to the 10th power, okay? So now we're going to cruise on to here. We're going to do 2 more. 1 more anyway. I'm really not liking this. I'm going to think of this as dz dx equals 1/2 x to the negative 1/2 minus x before I anti-differentiate that, okay? Then I'm going to say, oh, this must be z equals, well, that's x to the 1/2, and what do I multiply out in front of that x to get this half out here? Hey, it must have been a 1 minus, this is going to be an x. If it was a 1, it's now a 2. What do I multiply 2 by to get this 1 up here? Must have been a half there plus my c. Well, now I'm going to use x is 4 when z is 0. Well, I'm going to say, well, if z is 0 when x is 4, that's really the square root of 4 minus 1/2 of 4 squared plus c. Well, that gives me 0 equals 2 minus 8 plus c. So I guess this gives me negative 6, so c must be positive 6, right? So there's my c value. So I know my particular solution is going to be z equals, I can call it a square root of x minus 1/2 x squared plus 6. And that is the function from which that was derived going through that point. That's exactly what we're doing here, okay? And I got 1 more here, number 10, and then we're going to switch gears for a minute. Ooh, template. That looks like an inverse tangent. So, and I'm going to be picturing this guy as t to the 1/2 power as I'm cruising along. So my independent variable is t, okay? My dependent variable is s, so when I anti-differentiate that, I'm going to get s equals, this is my inverse tangent of t plus, well, that's 8e to the t, and if I take the derivative of that first one, I go here. If I take the derivative of that, I go there, plus this is going to be t to the 3/2. If I add 1 to that, I need a 1 in front times a 1. I need a 1 in there, so that's going to be a 2/3 here. So I better add my c. Now I'm going to come back and I'm going to use my initial condition of s is 3. What is the inverse tangent of 0 plus 8e to the 0 plus 2/3 times the square root of 0 cubed plus c? Well, that's gone. That's 8. Wow, ooh, where on the unit circle? What theta value gives us 0 for the tangent? That's right, that would be 0 equals 3. So that looks like c has to equal -5 here. And if c is -5, that means the function from which this was derived, s, you can make your funky little s's if you want, equals the inverse tangent of t plus 8e to the t plus 2/3 t to the 3/2 power. You don't have to write it square root of t cubed if you don't want to. And I'm going to say that's not plus anything. That's -5 this time because c was -5. And there's my function. Okay? Last one, well, it's not the last one, but we're going to solve the initial value problem using the fundamental theorem. Why are we using the fundamental theorem? Well, the reason we are is because I don't even know how to find the antiderivative of that thing, and you're going to be well on your way into Calc 3 before you're going to be finding that. So please don't type it into an online calculator and show me how to do it, because I know you're cheating then. Your answer is going to contain a definite integral if we are using the fundamental theorem. Ooh, we did this the last test, remember? Because we are going to define our function as an integral. We're going to say y equals the integral from somewhere to x. Now, remember, a lot of people screwed this up on the test. Okay, my x value is my a value. But if I have x up on my integral, I have to have a dummy variable, I'm going to call it in here, plus cosine. Usually, I usually use t, because the variable on your integrand on your integral cannot match your integrand, so that's a dt. But when I plug 0 into here, I need it to output -3. So remember, when I plug in a 0 into the x, this is accumulating right here, number 1, 0 area. And if I take the derivative of it, there it's sitting. There's a little f with x in it. But I need it to equal -3, so I'm just going to add -3 to it. And woohoo, I got it. Okay? Most people did a relatively decent job on that. However, just do not forget, please, because they will mark it wrong, these variables here cannot match. And the reason they can't match is if you're putting in an x, and you have an x here and an x here, you're not only putting an x in on the integral, you have to put it everywhere there's an x. That's why they have to change, okay? Otherwise, you're integrating a constant every time. And we're not doing that. So, what do we got here yet? I think I got two more, and then I'm done. So here's my derivative, and I do not know the antiderivative of that, and you're going to figure out, we're just starting these, you're going to identify with when you're not, but we're writing all these using the fundamental theorem. So I do know y is going to equal, notice I'm always leaving a little spot there, and this is going to be an x in there, right? Ooh, no it's not. Oh crap, did I do that one right? I did do that one right, because my independent variable here was x, so that's why I needed that guy up there. This next one, my independent variable is a t, so I got to put t up there, okay? And I'm going to put my a value on the bottom, and that means inside the integrand, I need a dummy variable. Now I can use x, dx. This is my derivative there, remember? And if I plug a 1 in there, I'm going to accumulate 0 area, but I need it to output 3 for my v, not my y. Look at your variables, Kruger. Come on there, big fella. And we need to add 3 to get to it. Okay, so this variable up here can never match what is in there. I can use whatever letter I want in there, okay, but it cannot match. It needs to be a dummy variable, okay? So we're cruising along. So here, again, cube root of tangent y. Absolutely no idea what that antiderivative is, but I do know that g, big G, can, and it's going to be in terms of y, is going to equal this integral, and I'm going to a y because I need a y in there, and I'm starting at my x value of 0 of cube root tangent. You can use whatever you want. I'm going back to t, okay, dt. These need to match. Those need to be in variable harmony. However, they need to be different from that one. Otherwise, I'm plugging in too much stuff. I need this to output a 4. So I'm going to say plus 4. And on the test, remember, we used this. I was very forgiving for those that matched variables on the integrand and the integral, but I could have taken more points off, but I didn't. I was kind of patient, and I didn't crucify you for that. And no, it does not matter if the 4 is added in the beginning or at the end, okay? So, yeah, you're going to have fun with these. That ends our lesson for today. Please work hard at these. Please, these antiderivatives, you need to know them all. You're going to be tested on them all. Make sure that you know, oh, crumb, you know all these. If you know your derivatives, guys, there's no sense in memorizing antiderivatives. If you know your derivatives, you back them up, okay? And then you're memorizing half of what you need to know. Print these off of It's Learning if you don't have them. Then I'm just going to shut up and say thanks for playing math today. I assume a lot of brains are fried right now, but we'll get through it. Ask questions when you got them. Have a good rest of your day, guys.